or a researcher or a developer of the various products for day-to-day use. Sir, we have got the direct recruit scientists, as you addressed earlier. In addition to that, there were a few batches earlier. Those people are also joining either online or here physically. And also the scientists C and Ds who are directly recruited through UPSC, they are also joining this program. Even some senior people are also joining, because all of us will like to
I have also joined
learn from your talk, and mostly so people would like to interact with you also, sir, and with your basic guidance, perhaps they can plan. And Secretary Sahab wanted also to know what is your vision, what is your mission, what you want to do, anything you want to add in the services of Minister of Arts Sciences, that also you can inform the Secretary Sahab. So let us take this golden opportunity to learn the maximum and to interact, clear the doubts if any, and plan for the future. So thank you very much. I will now request Secretary Sahab, if you want to speak something, sir, before you go for your lecture. Yes.
So first I will start with the lecture only, then
Okay,
maybe. So first I will give some something about numerical ocean modeling, because why I want to ocean modeling is it is same thing with atmospheric model. Numerical model means what are the things to do. I want to briefly tell about, and later on maybe I will talk about mission MoES, what we are expecting next 5 years and beyond. What are the observational requirements, or maybe science what we need to do, or maybe modeling or whatever we need to do, that I will highlight that. Then I will interact, maybe we can have some time in half an hour, we can a little bit interact. So I don't know, maybe formally I am not comfortable sitting here, I will go there only. So that I will. So hope you are able to hear us. The outsiders, those who are able to hear.
Yeah, switch on the mic.
There we can put it.
So hope everybody is able to hear me. So first I thought of giving something related to ocean physics and followed by the numerical model. But somehow I am not able to get time. So I skipped directly the ocean physics. But if it is time permits, maybe even after training also I can give. Because I have a course model for that one, which I have taken for what is called in Australia, one of the what is called, we had a marathon 1 month workshop, residential workshop was there. So I prepared and I made it for ocean physics, but I will make today only what is the fundamentals of ocean modeling, what are the components. But you always make the analogy of atmospheric model. But a little bit change is there in the atmospheric model, in the ocean model, because of the things what is needed for building the things. So I will first some of the things basic, I will start from model physics. Then once the physics is there, how do we solve? For that, we need to have some approximation. So what are the approximation we are planning? Then I will do about parameterization scheme. What is this parameterization scheme? That is really very important, which in India we never touch. That is important things. Then finally, how to set up the model. Then how do we force the model? Then finally, what is that running the model means, what it is. So that I will do it. So this is what I plan to do that. Maybe lastly, few slides about under mission MoES, what is we are planning. Not only mission MoES, in 2047, what we need to go from now. So that's, I will give a highlight so that you can think about in future what we can do. So when you talk about ocean modeling, of course, these are some of the main drivers. So always we look at it three fundamental parameters. One is temperature, salinity, and currents. We always look at this temperature, salinity, and current at different depth, that ocean. So how this present state at any point of the grid or any location, what is the temperature at any location, what is the salinity, if we know, then by knowing the current, we can understand what is the process is happening now and how this process will go. From this, we want to make how the heat and mass. Heat means temperature, mass means here salinity. How the heat and mass varies with the different time. That is what we want to understand total ocean in the entire ocean at different depth. Now for that, these are the three prime variables: temperature, salinity, and currents. The analogy to that in atmosphere is, of course, height, you know the pressure, then the temperature is temperature only. Instead of salinity, here it is a humidity. The mass components only change. The mass, of course, we know from humidity what is the mass, and from temperature what is the heat. So basically, we are trying to map the heat and mass. And instead of currents, you know the winds. So these three variables are the primary variables. From if we know at each grid point what is this temperature, humidity, and winds at different time domain, if it is known, then we will be able to know the present state of the ocean or atmosphere. Once we know the present state, then the winds are known or currents are known, then where it will drive the heat and mass, that is what we are trying to predict. So that is the major things. So roughly about 75 to 80%, you will be able to do if you know this, what is called temperature or heat and mass. Further, the second order, we have to go for ocean, we need to go for how the biology, phytoplankton, and how the chemistry interact, and how this biogeochemistry contribute to the physics, and similarly how the physics contribute the biology, that biogeochemistry will play a role. So that will be second order. So the biology, chemistry, and physics. The biogeochemistry will be coupled with the physics in the top. Then we will be able to know that biogeochemistry model, so that we can know, basically instead of temperature and salinity, we call as a tracer. The tracer component will be more here, maybe chlorophyll, phytoplankton, maybe nitrate, nutrients of various kinds. All these things we put into that, so that we will get more and more tracers. Instead of two tracers in the physics model, here there will be more tracers. Similarly, if you come to atmosphere, we need to go for aerosol, how the aerosol radiation things are changing, how the aerosol impact the physics in the radiation balance. Because of this radiation balance, how the temperature and the humidity and other things are changes, entire physics. So how the chemistry changes the physics, or how the physics modulate based on chemistry and vice versa. So this is a second order in the atmosphere. So essentially, we want to go for first order initially, then the second order, but still even first order itself, to understand the physics and other things, it is so complex in the numerical model or whatever the physics we can say. I will come back to that. And apart from that, we will have another processes. That is, suppose you afterwards you can have ocean and atmosphere coupling. First you have to do for this coupling, sorry. So this coupling and that coupling, then ocean atmospheric coupling, then further you have to go for what is the soil moisture and land surface processes, then how the snow and ice in Himalaya and maybe the hilly regions, and the ocean, maybe what is called in the polar region, how sea ice or ice shelf, how the ice shelf is changing. Of course, this is a short memory, that is longer memory. Then we go here, it will be much longer memory. So that depends on the time scale you want to predict. So I personally feel that even if you want to go for a few days, then only atmospheric model is good enough, forced with only SST, so you get the atmospheric model. That's what we do. And if you want to go for larger scale, then you have to go for ocean model, and these two are coupled. The ocean alone model, when you want to run, you have to have a forcing of this. That means how much surface flux you are giving, and how surface flux means both heat flux as well as salt flux, rainfall and evaporation. And based on that, of course, the momentum flux. All the three flux, if you give, the ocean drives the various currents, and how it heat and mass it changes, we know. Similarly, ocean alone, as our atmospheric alone model we want to run, you force with the SST and also maybe some places with the soil moisture, you post that. And of course, the radiation comes from the top. All these things put together, you can run the atmospheric model alone. But if you want to go for it, maybe a decadal or millions of years down the line, maybe 100 years or 200 years, then you definitely have to include the ice shelf model, how the ice shelf changes, and based on that, how the ocean changes, based on that ocean, how the atmosphere changes. That's what we need to do. So this is overall the main drivers for the Earth system. So we need to go for, always we are going for Earth system model. That is what we are. So presently we are doing only atmospheric model, but now for seasonal prediction, we have coupled with the ocean. But Earth system model, we should have this, at least these 4 components plus soil moisture and other things. When that is what Earth system model we look at it. Next one. Yeah, this is just a block diagram. So you have a Earth system model or a climate system if you want to know. So we need to understand what is atmosphere, how the atmosphere and ocean interact, how the biosphere and other ocean is interacting, runoff, and soil moisture and atmosphere. So these are the various components involved in the Earth system model when we want to do it. Just it is a just I want to know where are the components, because we need to go for Earth system based approach rather than only atmosphere, because we want to take care of various time scales. Next one. So when we talk about numerical models for atmosphere, as I mentioned, the main parameter is wind, temperature, and water vapor. These are the 3 variables will be acting. The external force, it is a radiation and the soil moisture. These are the 2 additional components will change. These are the forcing, solar radiation as well as the ocean, as well as soil moisture or snow and ice and biosphere. All this input will go so that you can get the total how the temperature and water vapor and the wind changes over the time. That is what we are modeling, trying to model in the numerical model. Go to next one. So similarly, in the ocean model, if you talk about, basically the ocean model, suppose you set up, assume that how to set up another thing, ocean model is there, you give the forcing. That means you give this much salt flux, that means this much rain, or this much salt you put it into the ocean, how it is diffusing over the time. And similarly, if you put this much heat, how it diffuses over the time. And then how it is ocean is dynamics changes. That is what we are looking at it. Basically, these 3 parameters, by forcing the atmospheric fluxes, mainly for salt flux and heat flux, as well as momentum flux, if you give, how these 3 variables changes over the time. That's what we are looking at. Next one. And of course, we need to, coupling means we have to do it. The main thing is here, it is a coupler. The coupler is what time we need to couple. That is more important. When they are talking each other. They're talking each other with ocean and atmosphere, at what time scale it talks each other, that is more important. Whether we have to allow, suppose some fluxes are coming from SST you are getting from the ocean, then you are putting to atmosphere for forcing the atmosphere is SST is very important. But at what time we have to give? In every 1 minute I have to give, or every 10 minutes I have to give, or every 1 hour I have to give. And similarly for the atmosphere to force the ocean, mainly fluxes, at what time interval I have to give. So that is what determines the coupler. So the coupler is main time is the time. At what time I have to exchange the fluxes between the ocean and the atmosphere. That is the main thing. So some of the developed people, they are more worried about coupler. This is very sensitive. Even though you may have good atmospheric model, you may have a good ocean model, but when your coupler is not good, then it will be a problem. That's why the coupler is more and more important nowadays. Next one. Yeah. Now I will come back to ocean model. First of all, why ocean model, especially numerical modeling? Why modeling? Of course, I want to have a difference between model and modeling. So first one is we need to go for scientific inquiry. That is the main purpose of ocean model. Suppose you want to have a SST is increasing. Now this SST is increasing is due to what? Whether it is due to atmospheric forcing, or it is ocean advection, or it is ocean mixing, what for it is changing, we want to know. We can do any controlled experiment, or even if you do, suppose if you have a cyclone, how much sensitivity of SST due to cyclone, if you want to do. So you keep SST is 28 and run the atmospheric model, cyclone model. Then you increase the SST by 28 or maybe 1 degree increase and again further increase. So sensitivity experiment if you want to do, That is what we want to know, because we want to understand what is the contribution of particular variables to the main system. In order to understand, that's why we need to have a scientific inquiry. Only we can do with ocean model. Our ocean model means atmospheric model or any numerical model. Second one is interpolate and interpret. Because we have a sparse data, observations are available here and there. We don't have a pakka everywhere grid, each grid we don't have a data. Unless we don't have each grid data, we cannot go for the next time step. So we want to have a interpolate and interpret sparse data dynamically. So for that we use this, basically we use this model. And of course that is basically once you interpolate and everything, you keep it, that is what almost it is analysis, or you can say that nowcast. Once you have nowcast, then you can go for next time step so that you can go for prediction. And of course, you all know that this is the main purpose, number 2 and 3. And of course, the last one is the observing system requirement. You maybe heard about OSSE. That means observing system simulation experiment and other things. That is, if you want to measure, where I want to measure, suppose I want to measure temperature profile, where I need to measure, where the variabilities are strong. At that place, you have to identify from observation requirements, OSSE model, so that we can put more variables. Suppose somewhere, even 100 square kilometer, there is no variability at all. Then there is no need to put observation everywhere. It is instead of putting where the variability exists more, so there we need to have more and more observations. So that is why we need to have where we need to put observing system of various variables. For that, we need to simulate ocean system simulation experiment. They call OSSE. So these are the main purpose we need to go for ocean modeling or any modeling, essentially for numerical modeling. Next one. Yeah, just I want to give this one. I want to distinguish between what is model and what is modeling. See, model is basically you go for engine level. So it means you have to go for, we can go for model physics. It is basically the mathematical representation of the ocean or atmosphere. That is what model. That is, you have a primitive equations, how the equations you develop, and also including what is called parameters in scheme. How do you develop? That is what model. That means basically it is a, I put an analogy of this one engine. I will come back to that. And whereas modeling is how to run the car. Okay, so just I am talking about only modeling, how to run the car. Somebody developed a model. Now for me to go from maybe from here to Agra to go, that is my objective. Okay, I don't require to go if it is engine is off, then the model physics fellow will help me. But my objective is to go from one place to another. That is my objective. For that, maybe I may be required to know only small things like a stepney change or something like that. But I don't require to know entire things of engine. If more problems are coming engine, I cannot. So the model physics is model, whereas modeling means how to run my model. That means somebody has developed, but I use for model for operational purpose. What earlier I was telling the 4 purpose I was telling, for that I have to use it. For that only I am doing for model. So here I am going to talk about only modeling. If you want anybody who are model per se for atmosphere or what is called ocean model, especially entire model physics from parameter and scheme and everything, that is a different, maybe different time I can talk about, but I will mainly concentrate on here is modeling. That means somebody has developed a model. How do I run the model? That's it. For that, what I require, like I was telling that how to maybe change the stepney or how to make something better system in the model. So this is basically a car. Model is a car. So if you are developing the car, that is a model physics. Whereas you run the car, it is this. So you should know what is your objective. Based on that, you have to choose. Next one. So now that's, of course, I was telling this, what you should know what is the objectivity of your model. What do you want to do with model? So first you should know your objective. Based on that, you have to define. Suppose you want to do for high resolution operational oceanography. That means I want a forecast for the next 5 days in the maybe coast of 100 kilometers in the ocean somewhere. Then what you have to do? Then some of the coastal application, something Suppose you want to, the sea level variation is happening. So how the tsunami or anything comes, how the sea level will change. For that different model, you have to do it. Similarly, if you want to go for a longer term forecast, suppose interannual forecast you want to do or seasonal forecast, for that what you need to do. So it's a different thing. So each, you have to choose what is your objective. Based on that, you have to define the modeling system. Of course, there is no one model to satisfy everything, so that we need to define your objective of the model, whether you want to do for short-term forecast, or you want to go for long-term forecast, or you want to have a global model, or you want a small coast. You are only worried about small coast. Then you have to be different way of working. You have to be. Next one. Okay. So first, when you want to run the model, the things to remember is number one, you should know what is the dimensions. What are the, of course, many of you know that in ocean model, if you do one dimensional, suppose you want to do something in vertically, you want to make it. Suppose I put out one place, some heat flux I put, how it diffuse, how the mixing is happening. So for that you want to develop, then you can do for 1D model. Or you can do radius 1 day in the atmosphere. You have one place, you have radius 1 day. So with that, you can try to simulate only one-dimensional model. So you can do that one-dimensional model. Then the two-dimensional, maybe river runoff or any of the barotropic model. I will come back to that. What is barotropic model is. So that if you want to do, then you can have a two-dimensional. Of course, if you want to have a full ocean in three-dimensional, you have to go for three-dimensional things. In ocean, usually they make it different notation than atmosphere. When you are talking about wind, atmosphere, you tell wind comes from where. That's what you define. But in the ocean, current goes to where. So it is to, whereas there it is from. That's the different thing you have to be always remember. But most of the things, if you want to develop a coastal ocean model, so usually they don't make it numerical, that means grid size of normal. They used for curvilinear or self or cross self direction. They define the x-axis and y-axis different way than the normal. I will come back to next slides how they define that. So I'll first start with one or two slides about the physics, how it is taught. Basically, of course, this is a Newton's second law. When you know that acceleration of the particle, it is basically the force by mass. That's the basic thing. So we are making the Navier-Stokes equation. The acceleration is dv by dt. That is what we want to know. Each grid point, what is the dv by dt of that parcel? We want to know the acceleration of the parcel at each grid. I mean, each grid means model domain, we call it 12 kilometer or 10 kilometers, that is a grid. So that each grid, what is the acceleration? That acceleration, basically, it is a combination of all the three. One is, of course, you know that Coriolis force. And second one is a pressure gradient. And of course, third one is a gravity. Then what is the tide? And the last one is a frictional. Frictional term here, it is called as a wind stress, basically momentum flux. So we have to give how much momentum you are giving and how much tide you have and how much gravity is there and how much pressure gradient. It is basically again function of temperature and salinity, how much density of water is there. Accordingly, the pressure gradient will change. So that pressure gradient term, of course, the Coriolis. So similar thing in the ocean also, atmosphere also, but only thing is the pressure gradient term, it will be different. And also you have a frictional term is different. I want to say one more thing to everybody. Actually, this is of course, this acceleration consists of all these forces. But similarly, you might have studied also in the atmosphere, what are the different Coriolis will be there, pressure gradient will be there. Of course, instead of tide, I don't think atmospheric tide is that much important because atmospheric tide is very small, but ocean tide is very high. That's why we have to include. And frictional force, maybe you have a different thing. In that, actually, very important thing is now this is whatever the Navier-Stokes equation you have, I think we need to incorporate very importantly in the atmospheric model Navier-Stokes equation. We need to go one more thing is called the electrical force. So recently I come across one of the article in the solid earth hydrodynamics. Solid earth also they are making fluid dynamics. That means in the magma, in the core, how it is making it. So there, the main dynamics, basically same Navier-Stokes equation, but plus they are adding magnetic force. So that magnetic force and the electrical force, it is more or less same electromagnetic force. I think it will be very important very soon. Maybe some of you can come out with the idea how to incorporate the electrical force also in the atmospheric model. Here it is not required. Ocean model, it may not be required. Just I am telling that we have to add the electromotive force also in this. Then only you can have a what is called atmospheric model with the, if you have a high cloud, okay, then the water droplet is there. Not only the dynamics, this is enough, but also your electrical force also is important, whether the drop has to fall or not to fall. So the electrical force is also important nowadays because the temperature is increases because of the cloud top or cloud heights are going on increasing. The electrical forces will be very important, which we need to think about it. So we can think maybe a little later in the atmospheric model when we discuss about it. So this is what we need to do. Basically, we need to solve this equation. Any equation, if you want to solve, you require how many unknowns are there in this. So that many equations we require. So that many unknowns equation, that many equations are required means that many unknowns, that many observations are required. So that is the ball game here. But this equation to solve, it is so complex equation. The number of variables required, this one is so enormous, so we cannot do. Hence, we make some assumptions. Okay, that is what the model error we are talking about. First of all, I told this is what, this is only for, I was telling the temperature, salinity and current. That will give even 100% if you are accurate, you will be able to predict only 80%. In that, again, you are started making assumptions. Okay, that is why problems are, we have a model anyway. It's the same thing, analogy to atmospheric model also, it will be a problem. Next. Yeah, so we need to have some, in order to solve that equation, before that, we should have some assumptions. So the number in oceanography, there are two main assumptions. Of course, partially it is in the atmosphere also. One is we have to have oceanus approximation. What is this approximation is, I will come back to that. And number two is hydrostatic approximation. Of course, the first approximation is not valid for atmosphere, whereas second approximation is valid for in atmospheric model also. And there are two other approximation, but that is pertain to specific purpose, not for general circulation model, but specific utility we need to use for geostropic approximation and the shallow water approximation. I will just highlight each one, what is that approximation, what it means. Next. So this approximation basically, the density gradient in the entire ocean, if you see that entire surface is very small. The density gradient maximum, it's roughly about 3% variation only is there. So the horizontal grid of one grid to another grid, the density variation is not much, or the mass is not much. Because of that, we assume that the effect of mass of the fluid can be neglected, but not the weight of the mass, the weight of the parcel. It is only mass of the parcel we are neglecting. And of course, if you multiply by gravity, then it will be changing. But that we are using. So that is the main approximation. Basically, you assume that this approximation is density variation are neglected along the horizontal grid. That means one grid to another grid, if any density gradient is there, we assume that there is no change. That is the first approximation we are making it. That is what this approximation. But this approximation is not good for when we are doing for acoustic type of tomographic type of modeling, where we want to have a sound signal and try to see where this sound will go and how it passes over the density gradient, there it is not valid. So only we can go use for Bosonic approximation is only used for large scale circulation model, that also in the large scale. When you are going for smaller, then it is different. So this is number one approximation. But whether that is valid approximation or not, that is different issue. But considering this is a only 3% variation, so that means now earlier assume that I am making it 80%. In 80%, again further down to 77%. If it is 100%, everything is correct. That's what we are coming. Next one. Then you know this is the atmospheric model also, you know that it is a hydrostatic approximation. Basically, this is a what is called the equation, the vertical. We are making this water column only will take care of this one. Basically, I think this is, I don't know whether you have studied this in the atmospheric model or anything. This is the same thing. When the vertical acceleration are very small when compared to the gravity. So we assume that approximation is valid, so that we can reduce the equation of whatever the Navier-Stokes equation when we make it. So we are trying to simplify the equation at least one direction. In the horizontal we keep it, but vertical we try to simplify, so that the number of elements or number of variables will reduce. So usually when you use for global and regional model, you can use for hydrostatic approximation. But when we go for eddy resolving or very sub-mesoscale about a kilometer and other things, then you cannot use for hydrostatic approximation. You have to use for non-hydrostatic. Of course, next one. So geostrophic approximation, this is same thing what you have, same thing you are using in atmospheric model. So it is basically the balance between Coriolis and pressure gradient. Same thing is applicable in the ocean, but it is required only whenever we require for specific problem to tackle. That time we should. This is for theoretical purpose, but it's not required for circulation model per se, geostrophic approximation. But for continuity purpose, I want to mention that this is the balance between Coriolis and pressure gradient. Next one. Of course, this is the equation also, you know that it is basically the function of pressure gradient and Coriolis. Next. And the shallow water approximation is basically, this is, as I told, this is you have an acceleration term in the Navier-Stokes equation, you have a Coriolis term. These are the only two terms will be there. Remaining, we are making it a change in eta. Eta is here, it is sea level. The sea level change anywhere in the ocean is basically a function of acceleration due to the water particle at each grid plus Coriolis. That's all. So why we use this approximation is basically, usually this one, we don't want to know, suppose if you put anything, temperature or maybe salt or heat flux, you put it in the ocean, it diffuse. The minimum diffuse time is required at least 10 minutes. In 10 minutes we required, when the model run, we have to run the barotropic as well as baroclinic time step. That barotropic you have to go for longer, very faster, and baroclinic will be having at least 10 minutes. That 10 minutes, I don't think that will change anything in suppose tsunami is happening. Tsunami is basically some place water displacement is happening. How this water displacement in one place, how it will amplify when it comes to the coast. That's what we require. So we want to only know about sea level rather than how the mixed layer process is happening, how the heat is changing, how the salt is changing. We don't need to worry about it. Only the sea level, how it is changing. That sea level is basically acceleration and Coriolis term. That's it. These two terms, if you know, I'll be able to get to the sea level. That's all. So that is what shallow water approximation. It is basically a 2D problem rather than 3D problem. That's it. This is what shallow water. This is basically used for a tsunami model and some other typical. Only we want to worry about sea level, then you can use this model. Next. Okay. So now when we talk about Navier-Stokes equation, that is one equation. If you make it to 3 direction, that means x-axis, y-axis, and z-axis, then that will be 3 equations. So 3 equations representing the change in velocity. That means acceleration. 3 equations. Now you keep one equation for conservation of volume. That means you, any entire ocean, you keep it, no water is going out or coming in, continuity. So that means you should have a conservation. So that equation, you have another equation. Then one equation representing temperature. That means temperature at the ocean changes due to what? So temperature at any location, if you take it about 100-meter depth, how this temperature at 100-meter depth varies? Due to what? Either it is due to mixing or heat flux or various things we have to do. That is one equation. I will show you that equation. And one equation representing salinity. That means how the salinity changes. Is it due to, it is basically a how much fresh water goes, how much evaporation goes. That balance is a salinity equation. And of course, one equation is represent density, because density is a function of both temperature and salinity. So these are the 7 equations called primitive equations. That means we should know 7 equations. That means we know 7 unknowns. So what are the 7 unknowns? How do we know that 7 unknowns so that we can solve this equation? That is what this modeling is about. Of course, in ocean, one extra equation is needed whenever you want to get the sea level. Suppose you want to have a sea level. So one more equation is needed. That is a shallow water approximation. That's why when you run the model, we run both baroclinic and barotropic together at the different time step when you want to have a free surface, that means sea level. So basically, these are the 7 equations how to solve and how to discretize into the numerical model so that we can run the model. Next one. Okay, as I told you, this is a Navier-Stokes equation, the first one. So that we are splitting into 3. Of course, one vertical component is hydrostatic approximation. We use it and go for it. So this is 3 equations. And the mixed layer temperature, that is a temperature equation. Basically, it is basically Q net minus Q penetration by rho Cp and H. That is basically how much heat flux you are putting and how much it is penetrating. And basically, it is a function of heat flux. Heat flux is basically both sensible plus latent heat flux. Net heat flux, how much? Then the advection. Suppose some heat place here and cold place here. If it is advected at that location, the advection due to how much it is coming. Then the vertical advection. Then the mixing. KZ, this particular term is mainly for mixing. Suppose you put this much heat in the atmosphere or anywhere, how much time it takes in, how it is mixing is taking place. Because of that, how much temperature is changing. And of course, finally, residual. Basically, the rate of chamber temperature is the function of heat flux plus horizontal advection plus vertical advection plus mixing. So all these 4 components, if you know the temperature. That's it. But this factor, if you know, you will get the temperature. And similarly, salt bucket equation, the first term alone will change. Instead of heat flux, you make a salt flux. That is nothing but evaporation minus precipitation divided by the mixed layer depth. That is H is mixed layer depth. So these are the 3 plus 1, 5 plus continuity equation, density equation. So these are the 7 equations we have to solve. This 7 equation, of course, this is available directly. You just make a numerical methods to convert in that one, so that you will get the 7 equations and you can make it. That is what numerical model is. So now how to run that one, I will tell you. Next one. Okay. I think before that, now we are talking about each grid. That is what's important. Now we know each grid, what is the velocity or acceleration. We know each term, what is acceleration. What is the square? That square is the model domain. Some place we are telling about 10 kilometer, some place we are telling about 12 kilometer. What it means? That means within the 10 kilometer, if anything is happening, I am assuming it's constant. How do I do that? That is from laboratory experiment. I keep one tank, there I put this much heat, this much salt, this much advection, then how it is changing over the time. So I make a mixing process. That means mixing processes, mixing of heat, mixing of salt, how it is happening, that I develop in laboratory model. Thereby, I develop some coefficient. Okay, that coefficient I put it so that if any heat advected to this cell, what it has to do? Certain things it has to absorb, certain things it has to throw in all directions. So that component only subgrid parameterization will do. Or you can say that, of course, these are the different terminology you know mainly. Basically, that is a process, turbulent closure scheme. That is, somebody has developed, this is the best method to use within this subgrid. Within the grid, what I have to do? There is no physics there. It is only empirical formula. That empirical formula, different people have developed different time, and they told that this is the best and that is the best, like that. So we have to do which one to plug into our model, which mixing scheme I have to use, that is I have to define. I have to come across. That means I have to do experiment with a different time. Even atmospheric, maybe cloud parameterization scheme. How the cloud condensation is happening, how the coalescence is happening, all these things basically a function of subgrid parameterization scheme. So that is basically people they used to do. First they will do laboratory experiment, then they call the DNS model, and then they call LES model or JD simulation model. From that they bring it that empirical relation. So that particular DNS and LES model, that is what I call as an engine. That means you have a car. In the car, you have engine. That engine, unfortunately, in India, we have not put effort to change the engine. If you are able to change the engine, especially the parameter scheme, you are able to change. You can call it as your own model. It is not required car. Car everybody makes. But my engine should be efficient in forecasting better way than others. That is what your parameter scheme. So everything is depends on like how good your engine is, how good your parameterization scheme is, subgrid parameterization scheme is. That is all depends on that one. Of course, somebody make a turbulent closure scheme, somebody make a convection scheme. There are many things are available, but I will next slide. Yeah, in the mixing also there are two things. In the ocean, we are talking about mixing. Basically, why we are in the cloud also we can tell that mixing, but here ocean is mixing means you put what I told in the ocean model, the flux you put heat flux or salt flux, how it is mixing. That is more important. So that is what this is doing. This how efficient you are mixing. That is what parameter scheme. There are one mixing is lateral mixing. That means one grid to another grid. How do I mix it? Suppose here it's salty and here it is low salt. How I do mixing between this cell? That is lateral mixing. And another one is top cell to bottom cell, vertical mixing. Suppose you put in the above, river is coming. The river water, how it diffuse, how it mix, that is vertical mixing. So how the vertical mixing is happening. So many people have developed. Suppose somebody has developed a PP scheme, KPP scheme, as well as the bulk mix layer scheme and Eller-Ramada scheme. There are many people who have developed different mixing scheme. So what you have to do is you have to plug in. You have a car, only engine you have to change it. Which engine you put it so that you get a better result in your area, that it is you up to you have to do it. So that is a ball game about the model. So basically the model is available. Now you have to change here and there the mixing scheme. Of course, if you are able to develop the mixing scheme, very good, but we need to put longer effort in that. That is more important. Because, yeah.
How do you differentiate lateral mixing with advection in reality?
No, advection is a particle is advected. It is particle is moving. Mixing means, suppose I have a heat.
Lateral mixing and horizontal advection.
No. Mixing is different than advection. Mixing means, suppose what you can say, if I put a heat, okay, in this cell, this is heat is advected to this one, or maybe you can radiate to the neighbor cell. So how it is diffused over the time, that is what. But whereas in the advection, the particle itself moves from one. This is a heat particle. That heat particle itself moves to another. That is a difference. So now the mixing is basically, now I put, suppose net heat flux is this much. Heat flux I am putting at the top of these things. Then this top SST, below that mixed layer, then below that how it is diffused. Particle will not move, but it radiates down the heat. So that is what the mixing. Right? You understand advection, and advection means the particle itself moves.
Yes, but I am just asking how differentiate in observation.
Observations, it is different. Okay, mixing you cannot do that, but actually you require fluid dynamics, very high frequency observation of that when you want to have this mixing observation. But particle observation you can do, because particle observation you put a color dye, then you can monitor how it is moving, that you can do it. But for mixing, you have to have a one order higher observation. It is about 1,000 or maybe I think 10,000 samples per second you have to make. So that is a very, actually it is a, that is what DNS they will. I don't remember what is DNS. Anybody knows? Actually, DNS is basically that exactly what you are telling is. See, we are talking about numerical model. Great. Further down is LES model, large eddy simulation. Further down is DNS. Actually, it is a fluid dynamics term in one small scale. How if you put one dye, how it diffuse. That is what all. So that is a main. Of course, it is a mainly fluid dynamics problem, very higher scale. So these are the various mixing scheme, lateral mixing. You can use it in the model. Next one. Of course, as I mentioned before that, when you want to do what scales, especially spatial scales as well as temporal scales, we want to resolve. What do you want to simulate? Whether you want to have for diurnal tides, or you want to go mesoscale eddies, or you want to have very large scale simulation for a climate model, then you have to go for time scale. So which one you want to use it, accordingly you have to select both the time scale. So that is what the space and time scales, you should know what are the variables. Next one. Okay. Of course, the same thing. What region we need to set up the model, we have to think about whether you want to have a coastal, or you want to go Indian Ocean, or you want to go for global scale. You have to define. And times. What time you want to simulate, whether you want to have a decadal simulation, or you want to have intraseasonal simulations, so that we have to define. And also you should know what is your compute resource available. Then of course, boundary conditions, initial condition, forcing, all these things we have to choose. So when you want to set up the model, these things you have to keep in mind. Where I need to configure, whether I have adequate compute resources, what is the boundary I have to use it, what is the initial condition I have to use it, what is the forcing I have to use it, what bathymetry I have to use it. These are some of the things you have to define, think before you start the model domain. Next one. Okay. So once you set up, you know, I want to set up, suppose Indian Ocean, or maybe North Indian Ocean, I want to set up. Then you have to define, actually, you have to define the grid space, what grid space you want. You want a 10-kilometer resolution, or you want a 100-kilometer resolution, you have to make it. But you have to make such a size. The main thing is you have to follow CFL criteria. The CFL criterion is the main thing, which many times we tell that computer, it is blowing up model. What is blowing up? Basically, you are not satisfying the CFL criterion. That means the velocity of the parcel, whatever the things are there, that is multiplied by time domain, time, that should be less than your grid space. If your grid space is, it is less than grid space. Suppose if the grid space is opposite or equal, then the model will blow. So that's why when the model will blow, whenever the model blows, then we have to reduce the time step. If you have to reduce the time step, but okay, I can reduce time step. If I reduce time step instead of 10 seconds, if I do 1 second, then your compute resource will go. So that is why you have to balance between CFL criteria. Initially, you have to, when you are running the first time, the CFL criteria you have to spend a lot of time. Optimum CFL criteria you have to choose. That means this is you have fixed. X you have fixed. You cannot change now. Okay, because my model domain, I want 10 kilometer. For 10 kilometer, what time constant I have to choose, and what is that velocity? You know what is the parcel velocity? Advection is coming how much? Then what time step you have to choose? That is very important. So basically, you know, more worry about here CFL criteria, whether the model is blow up or not, it depends on that. And next, of course, before that, see, when you are doing barotropic time step, barotropic means it is like a jet speed. It will go very fast. So you can make a second or below that. That is what I mean, tsunami model or anything. But baroclinic, you have to allow the time to mix. That means whenever I put new heat flux, I have to allow the model to absorb mixing. For 10 minutes, you allow to mix. Then you go for next time. That is what required for baroclinic. So baroclinic is every 10 minutes you have to wait and run the model. Then next 10 minutes, run the model. But parallelly, you will be doing an orotropic model also. So that is what we have to do faster. Next. So these are some of the, when you're talking about a grid, we are normally talking about a horizontal grid about 10 kilometer by 10 kilometer. So these are all mostly on finite difference scheme. When you're making a finite difference scheme, it can be regional model or basin wide or global. These are some of the typical example of model, ocean model. That is, MOM means modular ocean model, and COOPOM, that is the Colorado University's Princeton Ocean Model, modified Princeton Ocean of Colorado University, and the regional ocean model, and HICOM, that is another model. So these are various models. In the horizontal scale, it is all are same. It is a finite difference scheme. And this is basically how to solve one grid to another differential scheme. And the other one is when you want to come to the close to the coast, usually people go for a finite element model. That is a coast, suppose Mike model, they commercially available, and something at circ and other thing. And in the ocean, mostly they use for finite difference and finite element. They never use a spectral model like atmosphere. Why, you may be knowing that why ocean is not used spectral model. You know, spectral model is basically wavy, but in ocean, if you put a wavy, suddenly land will come. So you cannot put a wavy type of things. So this many waves, you cannot make it. That's why you cannot use, you can do, but nobody uses what is called spectral model for what is called in the ocean. Mainly they use for finite difference scheme or finite element scheme. Of course, in the atmospheric model, mostly they use for spectral model. They call as a T48 or T80. Depends how much wave number, depends on that you can difference. Next one. And the finite difference, of course, there are two things is to be remembered when you are talking about finite difference scheme. Two things we have to remember. One is whether your grid type is B grid or C grid. What is B grid and C grid? Basically, the definition of B grid and C grid is how initially when the model is there, assume that it's a model is a box. And each box you have made different verticals are there, some cubes are there. Now each cube, at what location I have to prescribe temperature, salinity, and velocity. That is what important. So sometime I can put everything at the center, what will happen? The parameter scheme, people, they tell that you cannot prescribe everything at the same place. So you have to put at the corner someplace. So in this B grid, T means tracer. Tracer means temperature, salinity, or maybe nutrients or anything you take it. That is a tracer, you put it there. And both U and B, okay, the velocity vector, you put it in another as a square. So that means when you put a square, everywhere you define UV, 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 and here you put a tracer. Tracer means either put a temperature, how much value, salinity, how much value. And whereas C grid, it is basically U and B you are defining opposite. That means U, you make it this direction, B, you make it like this direction. The center is a tracer. Of course, now there are sometimes good in B grid, sometimes good in C grid. It down you have to, like earlier I told, the mixing scheme you are using, accordingly you have to use which grid. Of course, when you select the model, suppose you are selected MOM model, okay, then you have to go with the B grid one. There is no C grid because that is all developed in the model itself. But now in the ocean model, everything uniformly they are coming out with the same grid, that is nothing but CQ. So everything is coming. Of course, if you want to have nested grid, it is different. And also we can have Cartesian or curvilinear grid also in the different finite difference scheme. Next. Why I'm telling is that one, if somewhere, if they specify it is a B grid or C grid, you should not worry about it. It is basically where you prescribe the tracer and the velocity. That is the main one. Of course, this is a finite element grid. So this is what we used to make. There, each grid, what is the conservation? And here, each volume, there it is only area. But here it is a matter of volume is important. That is what finite element model, you have to worry about model volume. Next one. Of course, as I mentioned, that spectral model is not usually done in the ocean because we cannot represent the wave in the ocean. Suddenly land will come, so we cannot do that. So not widely used in the ocean model, but of course atmosphere is reverse. Yes. Pardon? That's what, if you are having only, suppose Southern Ocean, you take it, then you can use it. If there is no land boundary, even there also, if small island is there, then it will blow. So that is, yeah, if you mask a land, there is no land, you remove the land in the bathymetry, then absolutely you can run the spectral model there. Basically, because of the wavy nature, you cannot bring it. That's the main idea. Okay, that is about horizontal grid. Now, when you come to vertical grid, we have three types. One is Z coordinate. That means each step 10 meter, 10 meter, 10 meter, 10 meter, you make it. And sigma coordinate, that is basically depends on the terrain. Suppose I make a total vertical level is 50. Okay. That 50, either it is 3000 meter depth or 30 meter depth, that 50 will be there. But Z coordinate, it is not like that. When it comes to here 30 meter depth, only 3 vertical level will be there. So that's the difference between the Z coordinate, Z coordinate, and sigma coordinate. And the layered isopycnal is depending upon the layer, it will change your coordinate. I think you are also having whenever, I think in atmosphere, whenever the mountains are there, how do you represent? It is I think it is an isopycnal coordinate. So same thing here also we can do them. Isopycnal coordinate. Basically, it is all topography based. How the topography is there, accordingly you can change. These are the three major things, but now most of the models are converging. What they are converging is usually large scale model, suppose global model, they use Z coordinate because they are more interested in large scale things. But now they are making it a hybrid. That's what one you have seen, HICOM. So HICOM is hybrid coordinate. So whenever there is a shallow water, you change accordingly. Our top layer will be more resolution, whereas bottom less resolution because the variabilities are less there. So accordingly they make it. Maybe most of the WARM model and also HICOM model, now it is called hybrid coordinate. Next. Okay. So now assume that you have vertical coordinate you have decided. You have a horizontal coordinate you have decided. Now you have to worry about where you want to run. Suppose you want to run only Bay of Bengal. Assume that Bay of Bengal. Now Bay of Bengal, you put a boundary. That boundary in the Southern Ocean, southern terminal, what do you want to do? Okay, so that is what this, whether you want to have a closed, that means you close. That means the water parcel advect towards southern boundary, it will hit and bounce back. Okay, but that is not good advisable. So that's what, but some location it is required, especially when the river and other places are there, that is required. So whether your boundary should be closed or your boundary is open means just you keep open any radiation, if it is, that means advection is going, you allow them to go out, but no new energy will come. That means after some time your energy will go. So it is also not good. But actually you can think of cycling. But usually the best one is you have to, or the boundary, you put a climatological value. If anything comes, then it will become climatology. That means southern boundary, you put a climatological value. So inside whatever is happening, when it comes to the southern boundary, it will become automatically the temperature and salinity up to bottom depth, it will change to the climatology. That's what they used to do. So next one. Of course, bathymetry. So you can see what is the topography. Basically, it is you have to take different sources of bathymetry, ETOPO or JEPCO. So which one is good for your region, you select accordingly. That is one thing. Next one. Okay. So now you have defined the horizontal and vertical grids you have selected and everything you have set up the model domain. Now, how do you run the model? So now, before running the model, basically what you do is, Suppose now again I will consider as a cube. Model as a three-dimensional cube. Now in this cube, what you have to do, you have to force. Okay. So each cube, suppose climatology, you have each grid cell, you have a temperature and salinity value, you have Levitas or anything. You define as per B grid, as per C grid, you define temperature of climatology, how much at that grid, and salinity of climatology at that grid, how much, and U and V you put 0. You understand this? Every grid you put a climatological tracer value and the velocity is 0. Now, once you set that one, now you force the model, apply the climatological heat flux, the climatological salt flux, the climatology of wind. So now you go on, do that. Then it will change. Over the period, it will change. Because of the heat flux, the temperature will try to alter. Because of that salt flux, the salinity will alter. Then it will direct here. Then it will try to move here. Then it will go on, change. Then finally, at one time, maybe for regional model and global model is different. At one time, there will be same temperature and salinity what you prescribe that will come. But now you will get another new component that is called velocity. Earlier you prescribed velocity 0. Now the velocity will be new. Why that new velocity? Because of the atmospheric force. So now that is the model they call as a cold start or maybe control run. That is the maybe that is called control run. Maybe next. So of course this is a what are the four? Suppose temperature and salinity is ready, then you have to force the wind forcing, buoyancy forcing, and tidal forcing. This forcing if give, then it will develop over the period. The velocity component also will be added. Next one. So this is what I was telling. Forced with observed temperature and salinity with velocity is 0. That is what cold start. Then you spin up. What is spin up? Spin up means you give continuously climatological wind forcing, heat flux, momentum flux, salt flux, go on give. After 50 to 100 years, if it is a global model, 150 years you run, then you will get same what you are given the temperature and salinity at that grid, same thing will come after 50 years. At that time, instead of velocity 0, you will get new velocity. So that is what cold start, that you keep it. That is what cold start model. So now, once that is ready, now you give the current heat flux, then you get the output current temperature or salinity. That's what it will be. That is what running your model, real-time forcing. Next one. Of course, the ocean assimilation means, that means before that, so now the cold start, you know what you mean. Cold start means you keep the temperature and salinity at each grid and give the fluxes. Then afterwards you get the velocity of ocean velocity. Then you give the current heat flux. If you give current heat flux, salt flux, and wind forcing, then you will be able to get the U, V, as well as temperature and salinity at any time. That means you can say that if you give me atmospheric forcing at any point of time, I will give the ocean data at any point of time. So that's why atmosphere drives the ocean. That's what we are doing. Now, that means it is almost nowcast. You give the present status of this one, you get the present status of ocean. Present status of atmosphere, you give it to me, I will be able to give the present status of ocean. Now, at the same time, you have observation here and there. So that you, as you know, that is the initial value problem. Now you have a nowcast. There will be some error in that nowcast. That error you try to modify with the new data set, whatever you got it from Argo or any other observation. Then the error you initialize with the, what is called observations. That is what assimilation. Basically, assimilation is nothing but the initial condition you are making it to close to the reality. That's what, so that your model will be error will be less. That's what you do assimilation. Next one. So this is overall concept what I'm telling you. You know, you bring one of the ocean model, you set up the model, then you give these heat flux and freshwater flux and all other things, then immediately you will get the nowcast. So you will get the current, temperature, salinity and sea level. But at the same time, if you have a temperature, salinity, sea level from the different observations, you assimilate the data, it is opposite, it is assimilated into the ocean model, then you will get the forecast. So whichever time step you want, you can go beyond that. Up to what time step you are able to simulate, that is up to you to decide whether good or bad. That means my model is good up to 10 days or maybe 30 days, like that you can decide depending upon that. So these are the usually different model is used, modular ocean model as well as the regional ocean modeling system. Basically, it depends on what time scale and other things are required. Next one. Yeah, of course, these are the various ocean models. You have a ROMS, CUPOM, as well as tsunami model. So what is the input for ROMS and other things? Freshwater, heat flux, wind you give means you will get temperature, salinity, current and sea level. Similarly, yeah, these are all circulation models. But whereas wave, if you want to know, that is a different model. That is basically, it is totally different model. Wave watch 3 and other thing. That is different type we can look at it. And tsunami is basically circulation model, but it is a two-dimensional. So it is called shallow water approximation you use. And of course, Mike is some of the things. It is a finite element model where you want to close to the coast, very near to the coast. You want to have very finest simulation that you can do with this. Next. Yeah. So with this, I will model. I finish it, but now if you want, maybe I don't know whether I conveyed correctly or not, but if you have any questions or anything, please feel free to ask. Then maybe afterwards I will take about 10 more minutes. Yeah.
Validation of models, what kind of data we are using for validation? Because in ocean, the observation.
Actually, in the observation, if you talk about, when you take AWS in the land,
Right.
similar analogy is moved bugs. Okay. When you take radio sounding, similar analogy is Argo. Okay. And when you take what else you have measuring AWS, radio sounding, what else you have measurement?
Radar also.
Radar. Radar. There is called coastal ocean radar, CODA.
Okay.
Okay. That will give up to 100 kilometers. You will be able to get the currents. So that data you can assimilate into the ocean model. Then satellite, you have a radiation and other thing, but here sea level you can get it, chlorophyll you can get it, and also you can get it SST. So all this data you can make. People usually make there is some subtle difference between assimilation and nudging.
Yes.
Assimilation is, suppose your model is coming, evolving, but my observation is here. Try to come to this.
Yes.
I am telling. That is what assimilation. But nudging means, no, you come here only. That means you are model, you are damping like you come to this only. So assimilation close to the real value. But here it is a real nudge. That's the difference. So there are many data are there, Argo floats and other things. And now it is also gliders are come. Glider data is available. So all this data we can assimilate. Usually when you assimilate, that data you should not use for validation. You should have independent observation to validate so that you can see how good it is.
So what about uncertainty, sir? Uncertainty is how we are dealing with.
Now you can
uncertainty.
sit. Now you can sit.
Yeah, what is that?
Uncertainty, sir. Uncertainty. How we are dealing with the uncertainty in ocean model.
Yeah, uncertainty, it depends on you, how, which model you are using. Yes. Yeah. So uncertainty is depends on you validate. Once you validate, it is too far from the reality. Then you have to worry about where you have done wrong. Whether your mixing scheme is wrong, or your assimilation scheme is wrong, or you have a what is called your approximation is wrong, or which there are many things you have to rework on it. Of course, each model is having how much uncertainty is there. We can always quantify that. That's one.
And for the coupling, sir, atmospheric ocean coupling, what are the important things for the coupler?
Coupler is main thing is time. At what time scale you exchange the fluxes? That's main. Still nobody knows whether I can do somebody make it every 5 minutes I exchange the flux. But if that is good, or you have to go for every 3 minutes or 10 minutes, that's the difference.
From online
Yeah,
participants.
I mean, so one question I have, like for weather forecasting over ocean, like most important data is the mode buoys. So, like you mentioned, there are where the variability exists more, we have to put the observation there.
Correct.
So, if we want to put more observation, like mood buoys specifically over the ocean in RSMC domain, which are the most important location which we should see?
Yeah, actually in 2004, we have done extensive study, what we need to observe in the ocean, where we need to observe, what type of platforms are required. Suppose where we need to put a mood buoy, where we need to put a Argo float, where we need to put a drifting buoy, where we need to have a XPT observations. So all these things, it has been defined by, as I was telling, that OSSC experiment we have done for the Indian Ocean. Based on that, we have made 36 location for mood buoy is the best location where we need to measure. That 36 location only, the Rama buoy is deployed. You know Rama buoy?
Yes, sir.
So that mooring is based on OSSC experiment. So this is the location highest variability in the ocean. So we put mood buoy. That's what we have put.
And in Arabian Sea, if we see, there are only few. If for the deep ocean, we can
Actually the
find few
variability
more
is in
locations.
the ARC fluxes, the variability, it is not much. See, especially the ocean component, subsurface. If you have up to 500 meter, the variability is very small. But this mood buoy is not only ARC fluxes, but also subsurface flux. So that is why they have to make it what is called something we have to do systematically. We cannot put everywhere because each mood buoy is very costly, and also not only costly. See, basically you have to avoid the shipping line. You have to avoid the maybe fisherman problem. So all these things put together, some of the things political reason, some of the things are scientific reason we have to think about.
Okay.
So that is why this 36, of course, that 36, 10 or 20 years before we started, how good it is, whether now it is very good or not. So we are really looking at, now there is a team in Clivor panel, they are working on it, OSSC for Indian Ocean, what is the best location now? They assume that these are the observations are available. So what we need extra, that we are working.
Sir, I have another question. Like you mentioned that for the dynamical models, like we have to force basically subscale process are being forced due to the parameterization scheme.
Yes.
And you mentioned that for electromagnetic forcing term should be added in the dynamical equation. So
Yes.
it cannot be added as a parameterization, right?
Yeah, it should be parameterization.
So which are the system that become more important for
According to my knowledge, nobody has been done. This is I am thinking we should add the Navier-Stokes equation I have written, no?
Yes, sir.
So the last parameter, we have to add electromotive force. That electromotive force is basically a function of electric field. So if you have an electric field this much, how much force it has to be created so that this acceleration term will change. That is what.
Yeah, mostly the models which we are utilizing are for specific application, like let us say GFS, we are normally seeing for the synoptic scale process, which is more important, although we are.
That is also
utilizing
when
it.
you are looking at a synoptic scale of a global model, you don't require it.
Yes.
But when you are regional or close to, suppose 12 kilometer resolution or 6 kilometer your resolution you are doing, where you have a convective activities happening, then you cannot ignore it. That's what I mean.
Actually, so the global electric circuit, the AC and DC component of the global electric circuit,
Yes.
that what you are asking about, I
Yes.
think. Because
Yes.
global electric circuit is present in land, ocean, everywhere.
Everywhere. Yes.
That component should be added, and how it is changing the atmospheric
See,
process.
global electric circuit in fair weather, that electric field is not significant it will not accelerate the force of the particle. That means the particle to accelerate, electric field is not sufficient in fair weather. But if it is a cloudy weather, the electrical force is sufficient to accelerate the parcel. We are worried about the parcel to accelerate, whether that electric force is sufficient, or maybe the electrical force is adequately more so that the particle will accelerate. That's what we have to see.
Sir, why, just a question, why we are not using the ocean model for the cyclones and other kind of extreme weather forecasting?
No, this is all I am talking about ocean circulation. For cyclone means then you have to have a couple with the atmospheric model.
Okay.
Usually, I personally feel that cyclone and other thing, the intensity more predominantly dominated by the heat source from the ocean. So you require heat content of the ocean. But the steering and other thing, mid-tropospheric things. So unless you don't have a coupling is not there, you will not able to. Actually, regional couple model is required for cyclone.
What is the role of the ocean coupling in the medium range weather forecast?
Good questions. So actually, medium range weather forecast, I personally feel that your mixed layer temperature is more important, not simply SST. You have to have what is the mixed layer temperature up to 100 meter or maybe 200, or maybe 70 meter, 80 meter. That temperature contributes more than the simple SST, because SST is a function of wind also. The mixed layer heat is different. So we should have I personally feel that if you go for tomorrow's in the ocean area, SST is good enough tomorrow or next day. But if you want to go for a medium range, you have to go for mixed layer. But if you want to go for seasonal time scale, you have to go below the mixed layer up to thermocline. That means maybe 200, 300 meter. But if you want to go for decadal time scale, then you have to go further down. But if you want to go to century scale, 2000 meter depth minimum is required. So that's what we have to. The memory is depending. If you go down, you will have oscillations of slow oscillations.
The depth of mixed layer that also influences.
Depth of the
Mixed layer.
yeah mixed
Because
layer. It is
changes
mixed.
from
Yeah,
basin
when
to
we are
basin.
talking about mixed layer temperature, it is a function of depth.
Yes.
So if the depth is more, the mixed layer temperature also changes accordingly. So it is a function.
Yes.
This climate change and the ocean acidification is happening.
Yes.
Is it an impact on the ocean model?
It's Switzerland.
Yes, that's what I was telling about this. I was talking about only physical model. When you want to go for that type of carbon flux, that means you want to have acidification and other thing, you have to include the biogeochemistry. So if you include the biogeochemistry, then only you will be able to see that whether acidification is dominant or not. So that will depends on biogeochemistry model.
Sir, like you said, for medium range,
Please.
sure. So for medium range forecasting, we should take then rather than SST, we should take that mixed layer temperature only. We
Yes.
should that
Yes.
will be more
Yes.
effective and interacting.
Yeah.
And one more thing, sir, that may be very basic. That CFL criteria setting. Why barotropic is faster time step and why baroclining is long? Because it is temperature is.
No. That's what I was telling. Barotropic means that the velocity goes very fast, like a tsunami model. The barotropic waves goes like a jet speed. So every second you have to sample. But the baroclining, it is basically a mixing has to happen. Then what is impact? Suppose you put this much salt or this much heat, then you have to allow to mix for 10 minutes. After mixing, you have to go for this. That's why every time step it. So whenever you model, you have to define in the ocean model what is a baroclinic time step, what is a baroclinic time step. You have to define.
Okay. So in the same model, how with these two means how because nothing depending on the system what I'm modeling, then on that basis I have to fix the CFL criteria.
No, CFL criteria, yes. Yes.
Whether I'm
CFL criteria, it depends on your what is called resolution,
Yeah.
spatial resolution.
that is the time step should not more than it should not cover one del x.
Yes.
Should not
So it depends on the velocity of the particle. The velocity, how fast it is.
Yeah.
If you know, suppose current velocity is 20 centimeter per second, then accordingly you have to choose the time step. If a current is somewhere, it is very faster,
It
very
will jump
high
more
current,
than one grade.
then you have to choose differently. But somewhere it is high current, somewhere low current. But your same model. So you have to compromise something. That's what.
Okay, sir. Okay.
That's why initially you have to train
Yes.
different time CFL criteria.
Yes. Thank you, sir.
Yeah.
So thank you, sir, for this nice lecture. I have two small questions, sir. So first is, I have two questions. First is, like, why go for a cold start when we can have the same results with a warm start? What are the advantages of doing a cold start? And the second question is, if there's a climatological model that says that ocean temperature is going to increase by, let's say, 1 or 1.5 degrees Celsius in the next 10 years, how do we know that it's not because of inherent biases and it is actually due to the increasing in carbon intake or other factors?
Yeah, the first question, sorry, what is the first question you can?
What is the advantage of doing a cold start when we
Okay.
can go for a warm
See,
start?
when the cold start, when you want to start, how do I start the model? Suddenly you set up the model. That means you have to define each grid, what is temperature, what is salinity, what is U and V. You don't know what is U and V. But in order to get the U and V and also model to stable, if that is actually some of the things I skipped. Basically, you have to see the kinetic energy, how it is oscillating. After the kinetic energy is stable, then your model is stable. To stability of the model, I put indirectly the same temperature, salinity, what you have prescribed initially, that same will come back after maybe 50 years. Okay. That means model is stable. Once you stable, then only you can do for warm start. For model to stable. Otherwise, simply suppose you can climatological temperature, climatological salinity, and also you put a climatological velocity, then you run, means model will blow out. So you need to have train the model. So that is why we have to run that cold start.
And so in the climatological,
Pardon?
like if the ocean temperature is increasing by 1 or 1.5 degrees Celsius in the next 10 years,
Yeah.
how do we know that's not because of inherent biases in the model and that all the temperature is actually going to increase?
That is what we have to do sensitivity studies. Suppose you change in carbon or something, you change this much, what is that is coming? Now this type of global large scale model, they try to see that you put this much carbon injection, then how much heat radiation is happening, then what is happening. So that are all will be taken into account. So finally only the error uncertainty itself 1.5 degree. So that is why they used to make it. So they have taken care of that one. Yeah, some.
Okay, Gayatri.
I just this is just I want to know. So our NWP are warm start or cold start? It is warm start, right? Because
Always warm start. First time when you set up the model, after CFL criteria is set, everything run, then you run the model, stability is happened, then it is cold start is over. Henceforth it is warm start. Once cold start over, model is ready. Now you give atmospheric input, you get ocean output. Similarly, in the atmospheric model, you give ocean input, SST and soil moisture or anything. Then you get the atmospheric variable like wind, temperature and humidity.
So in that case, how spin up is required? Means because we are already giving the real time data.
Cold start to warm start to go, it is spin up. That 50 years we are running, na? That is what spin up.
You know, in our NWP, whatever we are doing forecasting, we are giving real time data assimilation.
You are giving real time forcing and you are getting real time nowcasting.
Yes.
That's it.
So in that
You are not having any cold start, warm start.
Yes.
But who developed the model, ENSA people, they have set up, no? That time they will do. Now you are configured the model. Now, for example, NCM and WF, they are setting UK Met Office model. Okay. First, what they will do is this cold start. Until the cold start, warm start is over, the warm start model only they will give it to you.
Okay.
They will not give it to you raw model. Raw model means without, it is before cold start.
Okay.
So we'll take some questions. First, let us take some questions from, then again we'll come back to you. So those who are interested to raise, to have the questions, please raise your hand, and Mr. Krishna Mishra will take the names.
Shijo.
Yeah, Dr. Shijo Jagaria.
Shijo Jagaria is.
Respected sir, good afternoon. Thank you very much for the very informative talk, and we got familiarization with the model concept. I have, out of my curiosity, just wanted two questions. Remote sensing is on the advanced stage. Will the remote sense data be sufficient for modeling in future? And second question, what are the observatories or observation we should concentrate to improve our models? Thank you.
Your second question is answer to the first question. Maybe see more and more observations, either in situ or remote sensing. If you provide more and more observations, my initial condition I can improve. That means I assimilate into the model so that my initial condition I can improve so that my error will decrease. My uncertainty will reduce. So that is what the observation requirement is. So the observation always you have to think about two things. One is observation required for understanding the processes and observation required for assimilation. These are the two things. So more and more observation you put, suppose remote sensing data, I have various parameters, I have remote sensing data. I put more parameter into the model. That means my uncertainty will reduce so that my forecast accuracy will improve.
Okay, next.
Next, Dr. Swami Chakraborty has raised their hand.
Hello, sir. Thank you so much for the talk. It's very helpful. So I like to ask you about high resolution model when you were talking about this 6 kilometer model. So for atmosphere, there is a gray zone, mainly like it is very difficult to decide when we don't need the cumulus parameterization and when we should have a very high resolution model and we can just use that convection scheme without a parameterization cloud generation. Is that same for ocean when we are doing the ocean mixing, or means how we decide that we no need parameterization for mixing in the ocean for a high resolution model?
Yeah.
Thank you.
Yeah, actually, as I mentioned, it is more or less same. Cumulus parameterization and mixed layer parameterization in the ocean, it is almost same. So now if you have a high resolution model, if you want to know, some of the mixed layer parameterization scheme is not good. Something is good. That is why we need to various mixing scheme you have to train, and which is good you have to see, and accordingly you have to use it. Which scheme you have to use it. So it is basically like a which cloud parameterization scheme you want to use it for high resolution. Similarly, in ocean, which mixed layer scheme you have to use it for high resolution you have to define.
Okay, because like in the atmospheric model, they sometimes call that high resolution like 10 to 5 kilometer as a gray zone. So they are still like, though it is a very high resolution, still you use the parameterized scheme. So is it the same for ocean
No.
model?
Parameterization scheme, any model you have to use it. Okay, even 50-kilometer model, you have to use some parameterization scheme.
Okay.
Even if you are having 5-kilometer model, you have to use the parameterization scheme. But only thing is which parameterization scheme I have to use it for high resolution or coarse resolution, that you have to see depending upon after running.
Okay.
That is what we have to do. Cold start is important. So when you give a climatological forcing, when after 50 years you get the climatological same value, you get it exactly how much difference is coming, that shows your parameterization scheme is good or bad. So maybe the other question when you asked which one, whether we have to run the cold start or anything, the parameterization scheme, what I have to use, I have used correct parameterization scheme or not to say that only the stability of the model says. That is why we need to do cold start, spin up. After spin up, my model is good or bad. If it is a bad, you have to validate with the climatology. If a climatological and my model temperature is too far, that means you are something wrong. You have to change. Yes.
Next question is from Sudhir Dwivedi.
Dr. Sudhir Dwivedi.
Sir, good evening. It was very nice to attend this lecture. Sir, I had one, this one, like we are using coupler between atmospheric
Nigel.
and
What is that?
Idle means
Coupler is asking.
I am not able to hear
Please
it.
repeat your
Type, no?
question.
You can type.
Sir, actually, I had one doubt. Like we are using coupler between atmosphere and sea surface. So with the utilization of model like short range, medium range, or seasonal basis, are we going to change this coupler, or we are if we are changing these couplers, so which one criteria we used to follow while selecting the coupler? As a layman, sir, I am asking
Yes.
about just the
Yes,
basics, sir.
Yeah. Actually, it is a very good question. Basically, when you are running for a climate model, your coupler time scale between the maybe what to ocean and talking to atmosphere talking to ocean, once in a month you can talk each other. But if you want to go for intra-seasonal time scale, then almost you have to go for every what is called basically every 10 minutes you have to exchange. So it depends on what is that you want time scale. So mostly I personally feel that if you want to go for up to intra-seasonal time scale, you have to go at least 10 minutes. You have to exchange the flux between the ocean to atmosphere and atmosphere to ocean. Unless you are not going for a climate scale.
Thank you, sir.
Sir, no further raised hands. Sir.
Yes.
Again.
Actually, when you are taking about
Excuse me, sir.
upwelling, downwelling, we will be able to come. There is no problem because upwelling and downwelling, it is a function of not only the water parcel is coming upwelling, it is a temperature. So from the temperature only you can infer indirectly. Otherwise, ideally, when you are talking about upwelling and downwelling, basic things we think about the temperature, how it is changed. Sudden drop in temperature, that means it is upwell water or whatever the things.
Hydrostatic, you are saying.
See, whenever the scale, suppose if it is very small scale, that means then suppose if less than kilometer in the ocean, we cannot go for hydrostatic. You have to go for non-hydrostatic. Even atmospheric model, the 6 kilometer or 5 kilometer model, I am not sure whether you have to use hydrostatic. You have to go for non-hydrostatic. Then only because the density gradient, there is always upwelling, downwelling will happen. So that to take care, we have to go for non-hydrostatic only. Otherwise, we cannot resolve properly the system.
Yeah,
Dr.
Mr.
Srikanth,
Tuman.
Dr. Srikanth PS, RMC Nagpur. Please ask.
Yeah, good afternoon, sir. I'm Dr. Srikanth. So you were saying about the electric component and electric forcing of the parcels by electric field, no? I think the parcel will be charged by the ionic content. So by measuring atmospheric conductivity, can we start or advance in that area?
No, actually, basically, I'm talking about the acceleration term. Okay. So the electric force, basically it is a physics problem. I'm talking about very general. We don't know whether it is possible or not. Also, I'm not sure.
Okay.
Recently, I heard one lecture in solid earth. They are including electrodynamics in the Navier-Stokes. Why we cannot include? Here, basically the acceleration, whether the electrical force will modify the acceleration or not.
It definitely it will accelerate, sir, because of Lorentz force.
No, when that means when the electric field, suppose I have 100 volt per meter, electric field is there in the ground. So whether that is sufficient to change your parcel acceleration.
Yeah, but 100 volt per meter is too less.
That's why it is not. In fair weather, it will not.
Yeah,
But if you say that in thunderstorm is there,
exactly,
or inside the thunderstorm, so I have a strong electrical force.
Yes,
okay.
Correctly. Yeah.
If that electrical force, then we are only talking about dynamical force and thermodynamical force. Where is the question of electrical force? Why you are not incorporating electrical force? That means you are assuming that the electrical force is neglected.
Exactly.
Is it worth to neglect or is this worth to add? When to add, when to neglect? That is what my question is. I personally feel that if you are developing a thunderstorm type of model, when you are going for non-hydrostatic thunderstorm type of model, then definitely
in the Navier-Stokes equation, you have to add the electromagnetic force also.
Okay.
So that you have a gravity force, you have a dynamical force, you have a thermodynamical force, you have electrical force. So the unification of all the forces we have to include so that the acceleration of the parcel will vary.
So it is feeble magnetic force is also there, sir, due to earth magnetic
one?
magnetic force.
Yeah, electromagnetic means it is actually if you have a I'm not telling electrical force, I mean electromagnetic.
Yeah.
It is already unified, this force.
Yeah.
Actually, the physics, they are struggling to get all the four forces, unification of force. That is their thing. So we have to, of course, electricity and magnetism, it is merged, electromagnetic. Only now strong force, weak force, and gravitational force is a different force we need to unify.
Yes, sir.
Yeah, I think Suman, you want to, you can just come to the front and speak.
Good evening, sir. First of all, thanks a lot. You have explained beautifully in 1 hour to a non-atmospheric and non-ocean person, so we could understand that what is ocean modeling. My question
I am
is,
also not non-ocean person. I never studied ocean.
We got to know you are a very good teacher. Yes.
I am not at all, I have not studied oceanography. At least I have studied something in atmosphere, but not in oceans.
so we have not studied.
Yeah, I worked in ocean.
Oceans also.
Yes.
So, but sir, my questions may sound naive, but one generic question is like that when we talk about ocean modeling, so like we have different kind of oceans, we say Atlantic oceans, Arctic oceans. So when we do the modeling, so we do like this kind of spatial modeling that for, it may possible that, okay, for Arctic region, we may doing some modeling, or for Atlantic, we do, no.
No,
So
it is one more, all ocean is one ocean.
Ocean is, I mean, their characteristics are different, so their parameters.
Characteristics what? That's what
like
characterizes nothing but temperature and salinity.
Okay.
Of course, that is varies. Even Bay of Bengal, Arabian Sea varies. Northern Bay, Southern Bay varies. Paradip temperature varies between Chennai temperature, ocean temperature. So, but how much? That's the way. Arctic may be too much variation. Maybe here little variation.
Same models we are using with different characteristics.
Yes.
So now next question is, sir, like the model which we have studied, you said that we also studied the biochemistry also.
Yes.
Biochemistry.
Yes.
So in the second model, we are studying the pollutions of the oceans also.
Yes,
or
it is a tracer. See, basically what is that? The temperature you have, salinity you have. This is a particle, that means a tracer we call. So you put any number of tracer. You put a carbon, you put nutrient, you put a pollutant, anything you put, how it is affected and how it is changing. That's what we are looking at. That is what biogeochemistry.
Okay, so all the pollutants.
How many? Yeah, how many component you are putting, that many you can have. Even some of the biogeochemistry model that is having 60 traces. 60 instead of 2. In physics model, we are taking temperature and salinity. But in biogeochemistry, there are about 60 traces. So nutrient itself, there are many nutrients. So something is a phosphate, potassium, that, this, like that, so many are there. So each tracer, how it changes because of the dynamics, because of the physics of temperature and salinity.
How the advection and dispersion
is taking place.
Okay, and the third question is, like you said, when we talk about 2D kind of structure, so river runoff, you mentioned that river runoff. So how does that comes into the picture? I mean, how the runoff is coming into the oceans and it's playing?
Yeah, basically river runoff, when you talk about hydrodynamic model, you don't think 3-dimensional, no. It is only 2D. That means water is there, how it is going.
In oceans, how that runoff is
not only ocean, in the land also, it is not 3-dimensional, no.
No.
River model, if you are making it is 2-dimensional. That's it. Depth we normally we don't consider much in the river model. That's what. If you're considering, then it is 3-dimensional.
Thank you.
Madhulata.
Good evening, sir. This is Madhulata. Thank you for interesting talk on basics on ocean modeling. I have 2 questions. Sir, what is the accuracy of tsunami model forecast?
Accuracy in terms of sea level.
Sea level and the time of
arrival.
So spatial.
Yeah, actually, as of now, whatever INCAIS has set up, that is called N2 model. In that model, at least the time of arrival within maybe 1 minute, 2 minute difference. That's it. That means when an earthquake has occurred, in what is called Indonesian region. There is a displacement in water at that location. We know that. Then it is basically, it is barotropic model is very simple. There is no accuracy problem will come. The main accuracy will come, problem will come only in the baroclinic, where you are mixing. We don't know how to I mix it. Whether I have to mix it like this or I have to mix it like this, I don't know. That is why their problem error is in baroclinic, but not barotropic. Barotropic in terms of seconds. So maybe when your answer is in few seconds, sorry, in few minutes, within a minutes we can tell. In terms of sea level, it depends on how good your bathymetry. If you have a bathymetry is good, then you will be able to tell your sea level very good. If it is not good, then it will be accordingly, it will go. So that is why one of the biggest hindrance in tsunami model is how good your bathymetry.
Sir, I wonder, based on the tsunami model, are there any studies to explain the earthquake occurring over land? Because tsunami is also
No, what is that?
earthquakes over land and the tsunamis over ocean. This is just due to the movement, right?
Yes, earthquake only is.
Is there any studies that we can relate this with something happening tsunami over here and it can affect somewhere?
See, earthquake occur in the ocean, earthquake occur in the land because of the tectonic movement. If it is earthquake occur in the ocean, if it is a water depth, that means if it is a water depth more than 200 meter depth, so if it is earthquake, these two plates are moving. When it is moving, sometimes suddenly it will, like this, it move. If it is move, then the water displacement will come. That means 3 kilometer water, it goes up and down. So that means it is, you are just tapping the water. So it propagates the energy. So earthquake in the ocean, whatever is happening, if it is a vertical displacement of earthquake, when it is plate movement, vertical displacement, you will get a tsunami. So I am not getting that. Whatever the plate movement earthquake, what is happening in the ocean, it produces tsunami. Whereas in the land, it produces different thing.
Sir, I have one last question. If you see the atmospheric modeling, we have so much challenges for parameterization. If you see, it is cloud microphysics is more complex.
Yes.
Still, cloud microphysics is more complex
Yes.
for any type of
Yes.
cloud, particularly for thunderstorms. In the similar pattern, you explained 3-4 physics important for ocean. So, what are the challenges and what are the limitations in the ocean modeling? Like atmosphere, we have so many limitations.
So same thing here also. See, basically the mixing is how do you mix it? That is a major challenge. I think last week there is one JGR paper. How do you mix it? Because now suppose you put, that's what I was telling. You put, suppose 100 watt per meter square, you put it in the ocean. How much time it is taking to go up to mixed layer? That one, nobody knows. So that we need to measure. And moreover, basically we don't have in the ocean, what is your heat flux? Basically, how do you define the net latent heat flux? Basically, we are looking at the formula, empirical formula, but actual latent heat flux we are not measuring. Covariant flux you have to measure. So we cannot measure in covariant flux in everywhere, this one. So that observation if you have, then you can have a lab simulation, you have to do it. In lab, you put 100 watt in the tank. So how it is mixing, you monitor very high frequency observation at every millimeter you measure. So that one you have to make it to the parameterization scheme. So the basic flaw is the parameterization scheme, either cloud parameterization scheme or in the ocean, the mixed layer parameterization scheme. These are the two things very important. If you are able to improve that, I think you will have a major impact. So that is what we need to work about. I think we need to put considerable effort in developing the physics of the model. We have to touch the engine of the car, not only driving the car.
Thank you.
Yeah. You want to ask? Okay.
Okay.
So I think, okay,
Yeah.
Umashankar.
I just want to know whether coupler has, means when we are deciding CFL criteria,
yes,
whether coupler time has impact on this, means once spatial scale is fixed for different spatial scales, what is the whether coupling time will be different?
No. Coupling time, basically the ocean model CFL criteria is different. The CFL criteria for atmospheric model is different. Now the coupler is, suppose ocean model coupler is required. Atmospheric fluxus is there when I have to put it to the ocean. Every 10 minutes I have to put the ocean. That means I am eating. Whether I have to give 3 times a day or 5 times a day or 10 times a day, it depends on we don't know. Okay, that is actually every second I have to put, but every second I put, the problem is compute power. So that is why we need to do optimally what time you have to couple. Coupling CFL criteria is not, you no need to worry about. It is not at all required to worry about. Only CFL criteria is ocean CFL criteria how much and atmospheric CFL criteria stuff. From the atmospheric model, you make a fluxus. From the ocean model, you bring the temperature. So this temperature is this much is there, then the atmospheric circulation. Because of this circulation, the heat flux will produce salt flux and momentum flux, you put it into the ocean. So when I have to put it, every time I am putting back, what is the frequency? That is more important. This is not CFL criteria. Okay. So maybe, yeah, please. No, still some more is there, 5 minutes, 10 minutes.
If you want to interact further.
No. Actually, in my presentation itself, I have not covered. First, I thought in between questions I put. Afterwards, 4 more slides are there, which I have not completed.
Put it, sir. Can you put it again?
Yes. No, you can in between. Yeah. No, that is about basically I was telling about feature plan.
We can show, yes.
That it is not a numerical model.
Yes.
So what we need to do in the atmospheric side, that's all. Maybe 4 slides or maybe.
Open it, Krishna.
Quickly open.
Yeah.
Maybe 4 or 5 slides, maybe there. See, in the observation. Yeah. After the question, you click.
After the questions.
See me again.
Last.
Share it.
After the questions.
See me end पे जाओ. Question की बात है for.
Last. This is Mr. Mosam, no? You know, 100 project, budget. 2000.
Yes.
Wait. Yeah.
So anyhow, what I want to say is, you know that now ocean model, more or less same thing atmospheric model. Basically, our objective to improve the weather and climate forecast. As you know that we need to go to provide, this is our vision, what we are thinking about. Of course, one is we need to provide the best possible service, not only in the land, at sea and the air, all the 3 things, or maybe you can say that all 3 state of matter. So what we need to do is, we are thinking about now globally, everybody is thinking of Earth system approach because they want to go for short term, maybe few minutes lightning to climate scale. So different time scale you have to do, so that you have to go for atmosphere, ocean and polar. Polar will come into picture only when you are going for maybe ice shelf and sea ice inclusion in the ocean model, so that the ice shelf will matter. So now in this Earth system approach, I am always telling that these 4 pillars. One is we need to strengthen the observations, both in situ and remote sensing, and we need to understand. What is this understanding? I mean again, this is what parameterization scheme. We don't know still what time scale we need to observe. That means some of the high frequency observation is required to understand the physics of the processes. So that is what we need to, so the observation required not only for assimilation, but also we need to understand high frequency observations, understanding, so that we can do the better parameterization scheme. So number 2 is basically better parameterization scheme to develop. That's why we want to understand. And the third one is, of course, we need to improve our model. We need to improve our assimilation technique. Of course, we need to improve our or increase the high performance computing system. And finally, the forecast dissemination. We need to go for various ways of communicating the information to the society. So that is what we need. I personally feel that when presently this 4 above, if we do it, that is weather forecast. We are improving the weather forecast. But finally, we need to weather management. We need to reach in 2047, maybe some of you may be there in service. You should realize this weather management at that time. What I mean by weather management means simply if you want to take now weather is managing us, whether we can manage weather. For that, we should understand more. So we need to understand more. How much we need to understand more, that is the ball game. So suppose some opponent is there, you should know his weakness and strength. That means weather. Its weakness and strength we should know so that we can better prepare to fight with him. So that's why we need to manage weather means what we need to understand more and more. That is the first thing. Next. So in the observation, each 4 pillar, according to me, we need to do. In observation, if you see that we need to observe over the ocean, over the tropics and southern ocean. So these are the area very less observations are there. So we need to augment more. And also we need to improve both spatial and temporal and vertical sampling. I mean spatial, temporal, vertical means all ocean, atmosphere, both the places. So also we need to strengthen our AWS, radio sonde, maybe 1 order more. And also we need OSSC, that means ocean system simulation, ocean observing system simulation, we need to do it. That's what I was telling. I don't know where I have to measure the radio sonde, whether the present number of observation is adequate enough. We need to think somewhere where variabilities are more there, we need to augment. So that we need to think about. And also we need to augment various other form of observing system, especially drones. Especially drones are mainly very good for the boundary layer measurements, where we have a atmospheric boundary layer, and also where we can think of vertical wind profiler and a radiometer, so that we need higher temporal and vertical resolutions we need to measure. And we need to go for remote sensing. Maybe we need to have more and more satellites for probing vertical. Maybe the temperature, I was telling, we need to have temperature, humidity and wind. These are the 3 parameters. How many places you have, that much improvement in forecast. That's it. And of course, we need to test bed. These are the observations required mainly for understanding the physics or understanding or improving the parametering scheme in the existing See, now parametering scheme, somebody has developed in mid-latitude for Europe or that we are using. How it will be useful? You tell me anybody has developed a parametering scheme for tropical region? Nobody. Nobody will do. We have to do. Otherwise, it will be a vacuum. We have to put effort in developing our own parameterization scheme, especially tropical regions. And also we need to get the observation in innovative way, various other ways like crowdsourcing, maybe in IoT enabled sensor, some of the granular level, we have to go for it. And also we need to have various type of high quality winds and LIDAR and hyperspectral imaging. So these are the things I'm telling observation, but similar thing we required for ocean and polar regions. So these are the observational requirements we need to do. This observation and understanding and modeling, all these things I am talking about, this we have to put in place by 2030. The infrastructure has to be put in place by 2030 so that in 2047 you can realize or you can manage. And by 2035 you can think of whether what is called modification. Then by 2047 you have to go for management. From modification to management, go for next time step. Next one. Of course, these are some of the signs we need to, as I first itself, I told cloud processes. I mean cloud processes and it is dynamic means it is a cloud parameterization scheme. And teleconnections, we are more bothered about the zonal teleconnection, how IOD plays a role, how El Nino plays a role, but we are not having much information about how polar region influence the tropical and how tropics influence the polar. We are not knowing. So we need to have what are the teleconnections and the forcing, how the internal forcing and how much external forcing we should understand, how much linear and non-linear processes are happening. and various interaction between the atmosphere, ocean, and of course model physics, subgrid scale processes, parameterization scheme, cloud parameterization scheme in the atmosphere, and the mixed layer scheme in the ocean. And of course, atmosphere and ocean, we need to include atmospheric chemistry. So far, all the models are only atmospheric physics and ocean physics, not atmospheric chemistry or biogeochemistry. We need to add it. And also we need to develop this observing system simulation experiment. Next slide. And the model also, we need to develop vertical and horizontal model. We need to improve, especially in the tropic, and we need to go for a very high resolution model. But most importantly, the numerical model alone, as I mentioned, so much approximation, so much physics, what is called parameter and scheme problem, we need to depend on others. That is why we need to go for numerical plus AML based. AML based means it is also almost a statistical only. It is statistical and AML based, both are same. So we need to then, and more importantly, I am more very this one synaptic. We should not forget human intelligence at that time. Any numerical model, any AML model will throw something, but ultimately your human intelligence you have to use before forecast. That's why synaptic, numerical, and AML, all the three you have to combinedly use it. What is the system we have to use it, that we have to develop. And also we need to do for data analytics. That means many of the things, variables, we don't know where what is changing. So we need to have indirectly AML use technique so that where it is changing, what it is changing. And assimilation technique, the present technique, whether it is good enough or we need to go for better technique. And also location based forecast or hyperlocal forecast we need to plan. And also we need to go for various data, whichever format it comes, whether it is social media or IoT based crowdsourced data, how to assimilate that. And also we need to go for ensemble forecasting so that we can have an uncertainty we have to reduce. But where we have to use ensemble, that we have to use it. When it is cyclone or anything, if you do ensemble, but we have to see highest of highest order. When it is a disaster, we cannot average, means suppose if you do average, then it will become nothing. So we have to think about that type of ensemble. And of course, we need to think about, I think some of the youngsters I advocate now, some people put some effort on quantum computing. How do we use our models in quantum? It is not only CPU, GPU. CPU is mainly our model, numerical model we are using. GPU is AIML, but now quantum computer is coming. So how we can use the atmospheric model or ocean model in quantum computer, which we need to think about. Because definitely next to 10 years, quantum computer will play a major role. That time we should not be inferior to others. So we should, somebody has to put focus on quantum. And also we need to, of course, we know that how much compute power is required. And the last one is, next one.
Next slide.
Can
you escape karo?
Okay, so of course this is we are doing it already. GI based automated decision support means it has to give the AML plus numerical model decision. It has to give finally human intelligence I have to use to decide which one is the best one. That's where it has to go on. And maybe mobile applications. And actually we have to develop the trust to the user. That is more important. How do you develop the trust and strengthen our communication with the society? That is, I think we have to work out. These are some of the important things. And also we need to have data dissemination, also very simple, easily understandable language as well as terminology. And we have to think about augmented reality and virtual reality for that forecast. And this is what weather modification I just listed. So basically we need better understanding. Next slide. Of course, finally, we need to go for weather management. That time we need to think about what are the pros and cons, but also some of the ethical issues will be there. So what are the ethical issues we have to think about? Then finally, we need to think about even something called, if we go for better, what is called system in even weather war, if they are thinking about in future, even after 2 decades, then we have to prepare for it, how we can do that type of things. Next slide. So these are some of the outcome which we are expecting. maybe I think we need to work about our improved forecast. Finally, weather work considerations also to be in place. I think last. So this is for the last slide. Maybe we need to have some of the things, all the 4 vertical, we need to think about what observation we need, what understanding we need, what modeling capability, both numerical, statistical, and human intelligence, all these things we needed, and how our dissemination chain has to be strengthened with the user friendly. That is what we need to worry about. I think that's it.
Yes.
What I'm thinking, maybe we have to implement in 2047. So how we can transform, that is what more important. So that is in your hand, not in our hand. So that is why I want to make it. Maybe I will, of course, it is not the end of thing. I will maybe, I will continuously, at least for monthly once, I will try to come and talk. Maybe some other, maybe other areas of our subject. Then we can have a discussion. Yeah, I think this.
Thank you, sir. We are really greatly privileged, and we can say blessed, all of us, that we could listen from the horse mouth about the real truth, about the development globally, about development in India, specifically with respect to modeling. And also, at last, he has put off the vision, which has to be really followed up by you. All of you are the young. You will be there in 2047. So his dream will come true with your endeavor. And his talk today puts the foundation with you, that you will realize that dream, and his hope will come true and dream will come true. More or less, if you remember, Dr. Kalam says, ignite the mind. He has tried to ignite your mind. He has tried to ignite the young minds of India Meteorological Department, who have joined recently in the last 3 to 5 years. And you are in very preliminary stage, in the stage of scientist C, scientist D, some people are in scientist E. I am sure with his guidance, with his advice, with his blessings, entire Ministry of Earth Science will grow rapidly, and the vision which has been taken off towards 2047 in Samritkal will be realized before the time. And considering the mission MoES, which has been a flagship program with his leadership, where IMD will be involved to a large extent with reference to all the components what Secretary Saab has presented today. I am sure all of us will work together, will strengthen his hand, and will see that all the projects, programs under Mission MoES are carried out in time. So once again, on behalf of all of you, I express my deep gratitude and thanks to Secretary Dr. Ravichandran for his valuable time, energy, and dedication and commitment. And we are sure that he has told also he will take this type of lectures in future also. And sir, we will be always indebted to you
Next
for your
one is
time.
with the observations.
Yes.
Both observation, what are the various observations, not only ocean, atmosphere together.
Yes. So all people from outstations are also joining, and they have joined here. And you can see from the questions which have been asked by the young minds that they are eager to learn. So they are eager to learn, and they carry out your message. Thank you, sir. Thank you very much.
Actually, IMD, not only your main prime focus is operational forecast. Having said that, you should not, you should always develop what is the science developing in your area. So I would prefer 60% you focus on your operational forecast, at least 40% you have to learn new things. Then only you will be able to be with the evolving world. I think you have to outside what they are doing, how we can achieve. So you should have a 40% in R&D. Remaining 60% you put effort on operation, because you are operational. You are meant for operational. That's what we have to think of.
Thank you very much, sir, for your insightful words and the lessons you have given, sir. We will try to inculcate and try to follow all the things you have guided us. So we are very thankful, sir, that you have spared some time, your invaluable time and invaluable knowledge to share with us. And all the trainees are, sir, very fortunate that at the beginning of this course and at the end itself, you have been there. So their courses are ending this Friday, and they are going into exams from next week. So thank you very much, sir, and I thank DGM IMD for his guidance, persistent guidance for scientific pursuit and for motivation to all the younger minds. Thank you very much, sir. And last but not the least, I thank all the seniors and my dear colleagues joining physically as well as virtually. Thank you all. Thank you very much.
Right, now it's starting. Let it start. Yeah, start.
Sir, we'll want to have your next lecture before they go to their respective stations.
Yeah, when they are going, I don't know when.
After the exam.
No, but they, as long as this is there, they can always come
We
through.
would like to have one.
Yeah.
That is
End of November.
So now we can, Anup Miss there.
Lecture start.
Lecture we can start. Can you join the lecture?
Sorry, it is delayed by 15 minutes. He may be waiting.
कहाँ से होगा वो?
Vice Chancellor of SOA.
तो leave कर दो ना सर.
What?
They are organizing.
अच्छा.